control.
I'll do my best.
Rein you in a little bit.
The energy starts.
Indeed. Yep, should be good to go.
All right. Well, good afternoon, everyone. I see some new faces and familiar faces. Welcome if this is your first time here. I'm going to introduce our guest speaker today, Dr. Benjamin Johnson, alumni from this department. So just a brief bio, he received his Bachelor in Science degree in Physics from Oklahoma State University, his Master's in Science degree in Atmospheric Science from Purdue, and his PhD in Atmospheric Science from the University of Wisconsin, in 1998, 2001, and 2007, respectively. Since 2017, he has been a project scientist at UCAR, JCSDA, which is a Joint Center for Satellite Data Simulation, leading the Community Radiative Transfer Model, or CRTM, where he has expanded his expertise in all areas of atmospheric radiative transfer. Previously, he has worked as a physics professor at the University of Maryland, Baltimore County, and at NASA Goddard Space Flight Center on the Global Precipitation Measurement Mission, or GPM, where he developed snowfall retrieval algorithms. He has served in many roles, ranging from mission scientist in NASA field experiments, developing new theoretical models for hydrometeor melting simulations, serving as a member of several international working groups, and leading multiple collaborative efforts to improve community contributions to science and to accelerate the transfer of research to operations. His interests are varied, but focus around the topics of modeling polarized atmospheric radiative transfer, satellite radiant simulations, retrieval of atmospheric and surface properties, modeling complex media, and recently, applications of machine learning techniques to accelerate some of these capabilities. Now, without no further ado, Ben, take it up from here.
Next time I'm going to have ChatGPT generate my bio and make it easier for you.
Are you unmuted?
Yeah, let me.
More mechanic.
Just a second. Okay, can you hear me in the back? Thumbs up? All right, good. All right, so thanks, Myra, for the invitation. It's good to be back here at Wisconsin again. Had many classes in this room, and so it's nice to be back. Nothing's changed except for the chairs, so, and some bigger TVs. The projector's really nice, though. We had some really bad projectors back in the day. This is quite nice. So I'll talk a little bit about myself. I'll try to keep that very brief, but I wanted to give you some sort of background of where I came from after leaving Wisconsin, and then sort of what motivated me to do what I do now. And then I'll talk about the main topic of today's presentation is the CRTM, that's the Community Radiative Transfer Model. So we have many colleagues who've worked with the CRTM over the years. It was originally developed here at Wisconsin by Paul Van Delst. And then when Paul went to NOAA, he brought it with him to NOAA, and then I took over that project after Paul passed away, and I've tried to continue that in his spirit. So let me just give you some incoherent ramblings about me. I was born in Stillwater, Oklahoma. How many of you have been to Stillwater before? And were you storm chasing at that time?
No, I mean, I went to undergrad at OU, right? I followed the women's basketball team around.
Okay.
So.
It's kind of awkward, but okay.
I didn't get Eskimo Joe's.
All right. So what I tell other people is it's just southeast of the Armed Cart site. And they're like, oh, okay, yeah, that's safe. It's the Southern Great Plains site, so they know where that is. I got my bachelor's degree in physics, which how many of you had a physics degree for your undergrad? All right, so we have a good sampling here. Then I went to Purdue University. Well, that's where Grant was at the time, and so I think he was impressed by the fact that I had some physical knowledge, and he was happy to bring me on, and I really appreciate that. And then he was like, you know what, I'm getting a job at Wisconsin. You know, do you want to come along? And I was like, yeah, definitely. So I left a girlfriend behind and went to Wisconsin, and haven't looked back since then. So
Sorry.
No, you did me a favor. All right, so my career's progressed in kind of a weird way. So the very first project that Grant had me working on, he was like, all right, I want you to take this picture of a snowflake and digitize it, and then compute the scattering properties of that snowflake. And I was like, all right, I'll be done with this in a couple of weeks, you know. So I did it, I ran it through the program, and he was like, okay, that's fine, that was just for one frequency and one orientation of that snowflake. Now we gotta do it for all these different frequencies and all different sizes and stuff. And so 15 years later, so that took me to NASA, and then I started working on, you know, this sort of broader scale snowflakes gathering stuff. And then I was like, okay, fine, we can do all this theoretical work, but I actually want to go out and measure some. So I started joining in all these field campaigns. And I forgot one important one here, which was the TRIM LBA campaign, where, you know, sometime in 1998, 99, Grant was like, you want to go to the jungle of Brazil and launch some radiosondes, you know, for NASA. And I was like, yeah, sure, why not? What's the worst that can happen? Not speaking any Portuguese and going to rural Brazil, it's quite the adventure. So if you do get asked to go to some random weird place that you've never been by your advisor, you should definitely go, because it's an experience of a lifetime. All right, so started measuring stuff, joined into all these field campaigns that I could get my hands on. I was doing instrument science on board the University of North Dakota Citation II aircraft, which, for those of you who don't know, it's a pretty small jet, and it's quite wobbly when it gets into the kind of stuff we're looking at, such as convective updrafts. Especially during the MC3E, we sampled 25 dBz echoes in the aircraft by doing these spirals, and we're hitting the updraft, so it was quite impressive and scary at the same time. It's one of those things where you think you're going to die, and you're scared to death when you're in it, but when you land, you're like, I want to do it again. So that's exactly what that was. So I kept doing it. And so we were looking at, you know, ice particles like in situ. What do real ice particles look like? Because I've been doing all this theoretical modeling, and really wanted to get pictures. And I'm going to show you pictures of all this stuff later. I'm just giving you the nutshell. And then, all right, so given now that I've done the theoretical work and then the field experiment work, let's try to do something with this that's useful. So I was working with the PMM or the GPM group at NASA during this time, and started putting this information into the combined algorithm, which is combined radar and radiometer observations of the same physical scene, and trying to interpret the information that was there using this new knowledge that we had generated from all of this work, for the experimental work and theoretical work. But that was all fine, but that was kind of staying within the NASA community. We'd often write a NASA proposal saying this will improve weather forecasting, but it never really got outside of the NASA circles that often. And so I took everything that I knew out of NASA, took it over to NOAA and the Joint Center, and started working on the CRTM, where I can now actually finally implement something that has a direct path to operations. So, and that's what we'll talk about. A couple of things that I still want to do, this is a short list, is, you know, whenever you're doing a retrieval algorithm or you're doing data, you know, when you're looking at a satellite observation, it's a snapshot in time. It's a photograph, essentially, of something. You don't know where you're at in the processes that you're seeing, or that satellite image is sensitive to. And there's many different kinds of processes occurring, whether it's on the surface, in the atmosphere, clouds, precipitation, and so on. So being able to estimate what kind of process and where you're at in that process is critical to advancing state of knowledge. That's one thing. The other is uncertainty traceability. Is, you know, we make a lot of, you know, when we do a retrieval or do data assimilation, you come up with one solution to this problem, and as you know, that's pretty much not always the right answer, or you're getting the right answer for the wrong reason. So being able to trace the uncertainty from the fundamental sources, such as dielectric properties of snow or ice, and all the way out to your radiative transfer model, and then all the way through to your retrieval algorithm or your DA algorithm, that's critical to having a full assessment of the uncertainty of your chain of everything that's occurring. And that can help you find weak points as well and improve it. So those are the things. Here's some beautiful pictures of me and the aircraft doing various field experiments. This one, I was the same age as you guys here, the grad students anyway. That's me holding a very fancy radiosonde in Brazil. So, you know, a lot of my experiences in the field has taught me one thing, that human error trumps computer error, model error, because humans make way more mistakes than models do, and sometimes critical mistakes. And one example is, during a field experiment, we had the ER-2 aircraft, which is a modified U-2 spy plane that was loaded with a radar, and the pilot doesn't know anything about the science. He's an Air Force pilot. He just flies the plane. So one time he flew for 8 hours and he landed, and they realized they forgot to turn the radar on. So he flew 8 hours for absolutely nothing, at a lot of expense, and there were some heads that rolled for that. But that's the kind of things that you start to learn in the field, is that, yeah, we take field data or field experiment data as like fundamental truth. A lot of us, like that's the truth, that's the Bible, but it's really not true also. There's everything, every process that we do as atmospheric scientists has its own errors and biases and things. And the sooner you become aware of that, the better off you are, because it means that you're skeptical. You don't just take something at face value. You just develop your healthy skepticism. And I think that's our job, really, is to be skeptical at all steps of the process that you're engaged in. Trust but verify, right? So that's what I've been trying to do. So I'll tell you a little about the CRTM. It's been around for more than 18 years, but 18 years known as CRTM. Started in 2004. My team is Patrick and Chung here. They're both, they report directly to me, but we have lots of core contributors who are also funded to do CRTM work. We have folks over at GMAO, Met Office, Navy, and so on that are doing aerosol work that collaborate with us. And this is the tighter community, but there's an even broader community of people who contribute to this model. So what is it? It's a one-dimensional radiative transfer model that's vertical, right? Looks down, but it can do often Meteor views, but it just increases the optical depth. But it's still a 1D model. It's not a 3D model. It's used in numerical weather prediction, validation, satellite simulation, and it's the one and only radiative transfer model that's used across federal agencies for numerical weather prediction. So it's fast. It's designed to be fast, and the way it's fast is it uses lookup tables that are pre-computed. So you do as much of the heavy lifting offline as you can, and then you bring it into the model. It's also highly accurate, especially for continuous fields such as temperature and humidity, and looking at the ocean, things like that. We get down to about 0.5 Kelvin or less accuracy for simulating observations of a clear sky ocean for microwave and infrared. Visible gets a little iffy, but for infrared and microwave, do a good job. So it supports aerosols, clouds, precipitation, various gaseous species, and various surfaces. We'll get into a lot of that stuff. It's written in what I call modern Fortran, so it's not Fortran 77 at least. It's Fortran 2003 plus. We use some object-oriented methods. We use some more advanced methods to make it more generic, more user-friendly, and it's fast, right? So people have tried to write radiative transfer codes in other languages, but Fortran is really still the king of speed in terms of floating point calculations at this point. And it's highly parallelizable. Like, you can run it on millions of processors. We have OpenMP capability in there now, so it scales well when you're using MPI. So it's really designed for high-performance computing, but it can also run on your laptop. You can download CRTM and run the test cases on your laptop. I do it all the time. And it's really quite simple to use. And it's cleanly written, too. That's not my doing. That was Paul and others who contributed to it over the years, and you see in the history there. That has a legacy in compact Optran, which was developed by Larry McMillan and Tom Cleesby, he came to AMS actually and came to my poster, and I got to speak with him. He was one of the original developers of the adjoint part of CRTM, which I'm talking about now. So CRTM is not just a satellite simulator, it's also a radiance interpreter. So you get the forward model part. That's given the physical state of the atmosphere and the surface, you can generate the radiances that a given satellite would see, right? So if you fully explain the state, then you get the radiance that the satellite should see. But it also provides what the adjoint is. The adjoint is the derivative of the radiance with respect to the model state. And that's used in data assimilation, right? So it's that change, the change in the model state with respect to radiance that gets used to innovate the model based on the radiances that are being observed. And that's the most powerful component of it. Now the model adjoint in CRTM is hand-coded. So for every line of the forward model, there's a tangent linear and adjoint lines of code, and it's complex. It's challenging to write derivatives of code in code. So there's ways to do it faster, but I won't get into it. So these are what I call the management slides. Just a high-level reason of why it's important to do what we do. Satellites are expensive, right? We want to make the best use of it. And a lot of times what happens, especially in numerical weather prediction, they'll take satellite observations and throw out 90% of the data because they can't use it for various reasons. One, it might be too much data. Two, it might be because the radiative transfer model can't accurately simulate the radiances that are being observed from that satellite, so that it gets thrown away. Or there's memory issues and so on. So the CRTM, by becoming more accurate, can help improve this, but that's not the only thing. Satellites don't have a long time span, so the turnaround to go from observation to numerical weather prediction needs to be very fast, and you need to be ready to go on day one. And so that's part of the challenge that I have leading this project. A wide variety of platforms that's supported by the CRTM. It's mostly satellite radiance focused, although we do have aircraft-based support. You know, if you wanted to simulate something a little bit lower in the atmosphere, you can do that. The one thing we don't do is ground-based and upward-looking sensors, and that's just because of the way the CRTM is designed. It's not hard to change that, actually, because structurally the support is there. It's just the way we do the transmittance coefficients offline. But we support a wide variety of sensors. Many are sort of implied here and listed here there as well. A lot of NOAA NASA sensors, those are our primary clients, because those are the ones that are being used operationally. But we do also support a lot of these smaller groups like Tropics, GEMS, Tomorrow.io, if you've heard of that company. They're launching some satellites that have Ka-band radars on them very soon. So we work with, you know, these with agencies primarily, but we also work with partner companies and such. And the great thing is, I'll tell you more about it later, is CRTM is public domain. Anybody can use it, anybody can download it, they can take it and modify it however they want. And that keeps any one agency from trying to own it or trying to gatekeep it. Everything's on GitHub. It's public. You can go download it right now if you want to. And you can see exactly the research that we're doing. There's nothing hidden from view. There's no secrets there. It's all transparent. And I think that's the only way we can work moving forward, is that everybody gets to see what you're doing. If you really wanted to hide it, you can make a fork and then go work off on your own, and you can merge it back. But for the development that we do officially, it's all public. The fantastic thing about CRTM, and this is something that applies to many of you, is it's a direct path to operations. And you can contribute literally today. You could go make a pull request. That means you can go try to merge some code that you've modified into the CRTM, and that would make it into operations within a year, 2 years, whenever they go through their next update cycle. So this is really an easy way for folks to get something that they've done that's innovative into an operational system without going through the traditional gatekeeping of NOAA, NASA, and so on, because it gets used by all those agencies. And so if there's something that you're really keen on getting in, talk to me, and we're happy to work with you to get it in. So let's go into more detail on this stuff, but I just want to kind of highlight these key advantages. And then, of course, I mentioned earlier that it's a modern community model. So we, I mentioned transition operations. There's the collaborative development diagram that I spent like 20 minutes working on. What you can see is that there's a huge variety of inputs into the CRTM from all of our agency partners, universities, with grad students, Colorado State, grad students here working on CRTM. And so they can add their innovations. Those get reviewed by our team, and then they get put into the model and eventually get released after sufficient testing. By the way, please feel free to raise your hand at any time and interrupt me if you have questions or if I've said something wrong. I appreciate that. Just to sort of, I think this is the last slide of talking how awesome CRTM is. The number of citations per year since 2004 has pretty steadily increased over the past couple of years. I guess this is a pandemic effect. There's not quite as many papers written, but the general trend is increasing in terms of number of people using CRTM. The sister model in the European side is called RTTOV. That's the one that's used in ECMWF, UNetSat. Their project lead and we drink together a lot when we meet up. We're very good friends. So we collaborate a lot too. So we share information. So there's a lot of heritage between these two models that are quite similar, especially in the emissivity models. They've been around a lot longer than we have, so there's a bit bigger following, but starting to get people from Europe wanting to use CRTM because the code is cleaner, it gets updated a little bit more frequently, it's easier to use. So I think there's a lot of value in doing this, and we also try to make it very graduate student friendly, because this is the model that I wanted to have when I was a grad student, you know, because you can take it, there's a lot of support, you get it off the shelf and use it. So here's the sort of the highlight slide of the key technical abilities for the model. So we support UV, Viz, near IR, IR, sub-millimeter, microwave, and then eventually far IR with the FireX work that Tristan's doing. That's a lot, right? So that means that in order to do this, we have to support everything that is needed to do fully all sky, all surface simulations at all of these bands. And it's just 3 of us who are in the core team. So it really requires a community to do this right. And we have to be very specific about what we change and what we improve and what we spend our effort on. It would be fun to do snowflake stuff all day. That's what I want to do. But we really have to make sure that we're supporting the community and what the needs of the numerical weather prediction community are. So several species of clouds, and we have some microphysical model specific stuff that we look at. Multiple gaseous species, basically everything that's in the LBL RTM, that's a line-by-line radiative transfer model, which is the underlying model that we train our lookup tables from, support all of these species. Although typically in CRTM we support those first 5 or 6, maybe 7 species there, depending on what the needs are for the instruments.
Yeah.
Yep.
So ignoring the gap in the far IR, you're covering a huge amount of spectrum there. Does the model know that, okay, I'm in the IR now, or the near IR, and if you go to another part of the spectrum, it has to make kind of a decision to switch to a different mode of operation, or is it kind of a continuous, universal approach to the radiative transfer across the spectrum?
It's discrete, so it's based on it. So we simulate satellite instruments. So you can create a pseudo instrument if you want to that does exactly what you want it to do. But right now we simulate actual instruments that are in orbit or that are to be launched with those instrument characteristics, bandwidths, spectral response functions, sensor geometry, and channels, channel selection. So it's a channel by channel kind of thing on an instrument by instrument basis. Some people have asked for, why don't you just create a super generic instrument that covers the whole range of, it would just take years of LBL RTM running, I think, to do that correctly. But yeah, does that answer your question?
Yep.
Okay. Surface properties are a whole other challenge. Every one of these bullet points is somebody's entire, career, and even sub points within these are people's careers, and so that's why, that's the shoulders of giants type argument. The only way we can do this is by taking advantage of all the work that's been done leading up to this. Something that's relatively new in CRTM is active sensor support, so space-based radar and Lidar, backscattering and extinction. And then we also do support for non-LTE effects, non-local thermodynamic equilibrium that's higher up in the atmosphere, and Zeeman effects, but we won't talk about that too much in this talk. So CRTM is structured in a way that's kind of consistent with what you would expect based on what I mentioned before. The 2 main elements are the forward model, that's given the state, you simulate the radiances for that sensor. And the Jacobian model, that's the derivative of the radiance with respect to the model state. So those two elements are what you use in various frameworks. And then we have each module for surface emissivity, aerosols, clouds, molecules, and then gaseous absorption. So these are the main sort of physical models that one would be involved in. And each one stands on its own. You don't have to understand the whole CRTM to contribute to any one of these capabilities, right? You can just say, oh, I'm really interested in aerosols and adding a new dust species, and that's something you can do without knowing anything else about the rest of the model. So separation of concerns is important because it saves the people doing the research time. It saves me time from having to support it as well. I won't go too much into this, but there's been many versions of CRTM over the years. Right now we're on version 2.4, so we support a wide range of aerosol species. I'll list those in a moment. Multiple satellite sensors, operational ones like ABI, AMSU, ATMS, and so on, all the major sensors. And then version 3, which is coming up soon, will support full polarization, so full Stokes polarization. So you'll have the IQ-UV elements of the Stokes vector for each calculation that you do. But that means you have to change everything else that sits underneath that. You need to do that at the surface, where you're generating your polarized radiances, at the cloud level, where you're computing the changes to the polarized radiances as they interact with the clouds, and aerosols, and then you have to do that across that entire spectral range. So you can imagine the amount of work that needs to be done to do this. These green and yellow boxes are sort of where we're at with this model in terms of capability. And the first release of CRTM version 3 is coming up very soon. So if you're really interested in polarized radiative transfer in any context, we're happy to talk to you. If you want to contribute, please get in touch with me. In the near term, we're going to be focusing on the short wave, the visible radiances and near IR, because there's still some work that needs to be done there in terms of speed and accuracy. There's ways to get around that, like AI methods to speed things up, so we can talk about that later. So, some people are like, oh, well, why do you need polarized radiative transfer? If you're doing data assimilation right now, you're working on a limited amount of information content that just comes from the intensity of the observation. So the radiances that you're observing and the modification of those, you're just looking at the intensity but not directly at the polarization. By adding polarization, you're adding a new dimension of information content that can be exploited to give you more knowledge about the underlying physical properties. So what this plot is showing is that these are the rainfall rates greater than 1 millimeter per hour. That means these are clouds that are producing precipitation greater than 1 millimeter per hour. And the colors represent the polarization difference between the vertical and the horizontal channels at 166 gigahertz. That's a microwave channel that's sensitive to clouds, okay? So what this is saying is that there's information content in all of these clouds that can tell you something additional about the physical properties that are giving rise to these differences. Of course, it doesn't occur everywhere, but it's an additional thing that you could exploit. Furthermore, the radiances coming from the ocean surface are also polarized in the microwave and in the infrared, but microwave is where you really see the big differences. So the modification of polarized radiances upwelling through the atmosphere and interacting with the particles that produce these gives you a much more information-rich source to draw knowledge from. And the retrieval communities have been exploiting this for years. I mean, this was Grant's work for a long time, is exploiting that knowledge of polarization differences to interpret something about the clouds. But in data assimilation, you can do that for multiple sensors simultaneously and really drive your knowledge of the physical state much more easily. So how do we do that? All right. So I take a physically based modeling approach whenever I do anything, and try to do as much of the physical side as possible. So we start off with single particle properties. We start off with the individual snowflake. That was the first thing that I started doing as a grad student, was modeling something like this and then computing the optical properties. Then you can integrate that over some size, range of sizes, and then put that into your radiative transfer model and start doing computations. But if you're looking at a scene like that on the right side and you see those radiances, you really don't have any knowledge of what the actual shape of the snowflakes look like given that information content, right? So it's an ill-posed problem. It's the typical inverse problem where you can have a mathematically infinite number of solutions to that problem because a lot of things can fit it, and they may not make any sense at all. So you're trying to find the things that do make sense, so you're trying to constrain that problem a little bit. And by adding radar observations now with CRTM version 3, we can further constrain that because the radar really gets you much closer to the direct observations of clouds and precipitation. So how do we do this? You can come up with a wide variety of shapes of snowflakes. How many of you have ever seen any snowflakes that look like these on the left? No? Only if you've been flying in an aircraft at the very tops of clouds would you ever see anything like some of these, but it's super rare that you're going to see rosettes, although they're quite common. You just don't ever see them on the surface, and they're somewhat tenuous. So these are sort of idealized things. So in a sense, they become a way to tune your model. It's a tuning parameter of sorts because it gives you different degrees of freedom that you would not otherwise have with the traditional sphere. Because like all physicists, we like to start with the spherical approximation. Like imagine a spherical cow, right? That's where all physicists started. You're all nodding your heads and you know what I'm talking about. So the spherical approximation is the old way to do it, and now we're getting into this point where if you want to do polarized calculations using these particles, you need to know the real shape, orientation, things like that. So a lot of folks have been doing these physically based models, and that's the first step. The second step is to then compute the optical properties, like how would the radiation coming from the surface or clouds or from the particles themselves interact with particles that are shaped like these, right? What does that do to the radiation? How does it modify the polarization or the intensity? And that's a trick. And then even more, what happens when it starts melting, right? So for those of, how many people have done some radar research, you're familiar with the melting layer, bright band, right? So the bright band comes from melting snow or ice particles, and it really kicks off at really small melt volume fractions. So what this is showing is melt fractions going from 0 to 1, from a pure ice particle down to a perfectly melted particle. These are my simulations that I did quite some time ago. But what I show, and I'm not going to show you here, but is that even at 0.15 melt fraction, where the particle still looks very much like a snowflake, and most people would say that's still an aggregate or a snowflake, it looks like liquid water in a microwave. It just looks like big water, and that's where the bright band enhancement comes from. You just basically have big water from the radar point of view, right? So you get the stronger backscattering signal from even a little tiny bit of water on there. It's really impressive, and the extinction kicks up very rapidly too. So that's one thing CRTM is missing, is this melting model, and that's something that I'm going to be putting in over the next year or so.
Ben, what was the numerical simulation technique you're using on these particles to do the radiant part?
The radiant part, so I used the discrete dipole approximation, or DDA. It's slow, but very accurate for these kind of things. So basically you discretize these particles into little tiny spheres, and then you have dipole-dipole interactions. You're computing the far field effect based on those interactions. And then it's a combination of water and liquid, and so the liquid has a different dielectric property than the ice, and so that allows you to have that discernment between, whenever you start having that small amount of liquid on there. So I won't go into too many details. All right, so equations. All right, this is going to be on the test. Are you ready? The main thing I wanted to get out of this slide is that typical models produce something called a mixing ratio. So a numerical weather prediction model just gives you a mixing ratio of ice or liquid water, right? It says, oh, here's the ratio of ice water content here, here's the liquid water content. And then it's up to the radiative transfer model to actually do something with that to simulate what the satellite would see for that given mixing ratio. It's a challenging problem, because you can imagine if I give you a bucket of water and I say, distribute this in any number of possible ways to simulate what a satellite might see, it's going to take you a while, right? So they're giving us a bucket of water, and we have to decide how to distribute that bucket of water in a way that makes sense for a satellite simulation. So the red items here, Q is mixing ratio, rho is density, NT is the number of particles in your simulation, right? That's what comes out of your numerical weather prediction model. CRTM has to come up with all of the blue numbers based on that information. These equations provide a specific analytical formalism to go from what the model's giving you to what CRTM needs. So if you make this assumption of a gamma distribution, you can come up with an analytical solution to that, and that's really elegant. But it's not true, of course. Real particle size distributions don't follow a gamma distribution or an exponential distribution, but we always like to pretend that it does because it's way easier to work with. Otherwise, you're working with real particle distributions, and it becomes quite messy. So we do these as a fitting mechanism to what reality is, because we don't know what reality is unless you're literally flying a plane through every part of the cloud and sampling it, which is also impossible because the cloud changes as you're working. You can also take a lot of field experiment data and use that to generate a variety of possible ways to distribute this water in different size distributions. So these are size distributions taken from Brian Baum's website a long time ago, where you have a huge set of possibilities that you can draw from to help you generate tables that you can then use in your radiative transfer model to more accurately simulate what kinds of systems that you're seeing when you're doing a retrieval or a data simulation problem. It's just zooming in a little bit here to show you what kind of things you can get out of it. So one would be like the dispersion parameter, that's the mu value in your modified gamma distribution, or you can just get the numbered densities based on some observations from those experiments. And so, of course, each experiment has their own sort of characteristics. One of these can't do justice for the entire globe, right? because precipitation is different over the ocean, over the land, so on. So you need a wide variety of things that you can sample from. And then you have to start making some simplifying assumptions on the model side about what the microphysical properties are. So for example, Thomson microphysics, how many of you have used like a microphysical model like Thomson or GFDL, WSM6? Okay, so these microphysical models start to try to make some of those assumptions about how that mixing ratio gets converted into something that's more realistic in terms of a distribution of mass that you could use precipitation calculations or in the rate of transfer. Greg Thompson joined the Joint Center recently, and he's been working with us to help improve this relationship between what's assumed in these models and what CRTM assumes. You'll get all these slides in Grant's class if you haven't already. But so you recognize the typical optical properties that you would compute based on this information. So I mentioned that we have the particle size distribution information, that's the blue stuff. And the red things are the single properties. So you have a snowflake, you compute the optical properties for a single snowflake. That's what goes into those reds, and you integrate over those distributions to obtain something that you would use in your radiative transfer model. So I won't go into it, but I left it here for those who want to get a little bit deeper into it. Furthermore, you need to make some kind of physical assumption in your calling model, like the particles that are being created in your microphysics model need to be consistent with what's being assumed in your radiative transfer model. So we're calling this physical consistency, right? If they were looking at cirrus when they generated their microphysics scheme, the CRTM model should also have a similar relationship. It's not a guarantee of success either, right? So just because there's physical consistency doesn't mean that it's going to give you a more accurate result when you compare to observations. And that's a challenge, right? That's where you get into the sort of the uncertainty and the playing around of things, and you start playing games with the knobs that you have available to you. So these kind of updates were motivated by the fact that we observed that when we would do simulations of microwave radiances, and that's what you're seeing here on the bottom. The left is an observed image of a microwave channel, I believe it's 89 gigahertz. And on the right is a simulation, and you see the blue colors are colder radiances. That means there's too much ice, or there's too much scattering from the ice that's there. So what's causing that? Was the model wrong? Was the CRTM wrong? Was it some combination of both? It's some combination of both, almost always, right? So the model is usually wrong. It puts a cloud in the wrong place to produce too much ice. The CRTM is also wrong because it might be interpreting those ice particles as snowflakes instead of graupel or so on. So this is really the challenge, is to get something that's physically consistent, something that gives you results that are similar to your observations. So here we have the SSMIS observations on the left at 37 and 183. And then if you assume spheres, that's the middle column, if you assume every single particle in that scene was a sphere, that's the result you would get. If you assumed every single particle was a snowflake, the answer on the right is what you get. The reality is somewhere in between, right? It's some combination of those, and if those of you who look at snowflakes in real life, they're not all spheres, and they're not all pristine, beautiful snowflakes either. They're amalgamations, they're aggregates, they're broken pieces, and it's just a huge range of possibilities. So that's why I was saying it's kind of a tuning parameter in a sense, because it allows you to have more degrees of freedom whenever you're doing these kind of estimations. So I won't go into too many details on this, but so we call this part of the CRTM the Community Hydrometeor model. That's because there's a broader community of people who just look at hydrometeor properties. They look at how do you model the physical properties of snowflakes, of aggregates, of ice crystals. And then there's another community that takes those physical properties and then computes the single scattering albedo, the asymmetry parameter, and so on, the things that are used in radiative transfer models. And so we're trying to produce a common framework for accessing, interpreting, and utilizing these kind of properties. Here's an example from the Texas A&M group, that's Tong Ren and Ping Yang's group, showing that their recent model can produce things that are actually useful. So this is showing snow water path along some transect here. These are the effective radius of the snow particles, and you can see there's a range of radii from like maybe 200 up to 1600 microns effective radius, and then the rainwater path below it. So they separate their database into snow and rain, And then if you do some radiative transfer calculations, which is shown on the right side at microwave channels, so 166 and 183, you see that the observations, which is the blue lines, quite closely matches the CRTM. Of course, there's some differences. There's a little bit of an offset there. But you can see that we're getting sort of the range of variability that you would expect based on these new databases. So it's an iterative process. It's kind of a slow process to eventually get to things that look consistent. And this is actually quite good compared to what we've seen in the past. So it certainly beats spheres. And it's using some of those non-spherical particles that I showed before. So we're getting closer and closer to things that are repeatably more accurate, more consistent with what we observe. So I talked a little bit about passive radiance simulation using CRTM, but we're now able to do active radar simulation. So on the top, we have an observation of radar reflectivities. Let me use an analog laser pointer here. So these are observations. This is altitude, and that's along some transect. You see here, this is the bright band. So that's where the snow layer is melting into the rain layer. And the CRTM simulation, given the same thing, produces something that's really quite consistent with that. We get the snow layer quite well, we get the rain layer quite well, without any special tweaking. There's no modification. We just take the retrieve parameters from the product that was retrieved from these products, put it back in the CRTM, and spit out the reflectivities given that information. Now, that's sort of a mechanical check. That's what it should do, actually. But what do you see that's missing? That's the melting layers missing, and that's the one key part that I need to get in there, because it impacts everything else below. It impacts the attenuation, reflectivity, and so on. So, but not only do we produce the reflectivity, we also have the tangent linear and adjoint components for each of these simulations. So we know what the first derivative is with respect to the model state for all of these. And then these are the CFADs for those of you who like looking at CFADs for those. So the top is the observed, this is KU, KA. So the simulation, not quite perfect. We overestimate in some areas and underestimate in other areas, but it's really quite close. We're very happy with the capability right now. It can still be easily improved if you're interested. Here's a CloudSat example. These are observations through Hurricane Bill. This is the flight line that starts here, crosses the eye, and ends here. So you see here, this is the eye. And these are observed radar reflectivities from CloudSat. Again, the observed reflectivity, and these are the simulated reflectivity from the new CRTM simulation. A little bit overestimating the reflectivity, but that's something that can be modified through the microphysics that I was discussing before. But I'm really, really encouraged because we can capture the whole range from the relatively low reflectivity items all the way up to the highest reflectivity items, and get the attenuation out of it, which is shown there on the right. That's incredibly useful for data assimilation, because if you can assimilate the reflectivities directly, that tells you exactly where the clouds are, exactly where the precip is, right? Which has been a major challenge for all kinds of cloud-type models. It doesn't always know where to put the cloud exactly. With this, you'll know exactly where. Go ahead.
So, please, for the bottom panel on the left, so we have simulated reflectivity values that are higher, up to over 20 dBz or so. Is that due to the attenuation correction? Is that why they're higher than
No, so
in the above panel?
no, it's probably due to the fact that we're overestimating the reflectivity in those regions, just based on the assumption of the particle microphysics, or there's maybe too many particles there too. So these are first light images. This was published recently. But this is where you get back into the science. So you build the instrument, you build the capability first, and then you get back to the science.
Yeah. So the CRTM, can you simulate reflectivity below where the DVR can register? It's like 2 kilometers or so?
I'll repeat your question. So he's asking if you can simulate below where the DPR can't see. So the DPR has a fairly high noise floor. It cuts off at about 12 dBz. So you can, actually, because your profiles, if your profiles have the information in it about the precipitation, you can simulate what it should have been able to see if it had a lower emissivity. So if you get profiles from another model, right, so like a numerical weather prediction model that has your height and medians all the way through, you can still simulate that, right? But if you're trying to match what the DPR sees, then you would want to impose that cutoff, maybe, depending on what your goal is. But by adding additional false information, it doesn't really help you that much with any kind of data assimilation or retrieval. It'd be nice to see, but it's probably not adding any new knowledge to the problem. Does that make sense?
Yeah.
Right, because what you're really trying to do is extract the information content from the observation, not generate something that you can't observe. Again, if your goal is to just interpret observations.
So just to clarify the interpretation of that left slide, the left portion right there, the top is the actual observed
Yep.
Reflectivity. The bottom is a simulated reflectivity using a retrieved hydrometeor profile from the first, or how are the two related?
Okay, so in this case, Isaac Roddy at GMAO, he did this work, not me. He used actually model data to do that. So these aren't retrieved. These aren't the retrieved properties. These are from a model. These are from a model reconstruction. So for those of you who've looked at this kind of stuff for a long time, this is really good.
Okay,
Because
so the second is completely independent, or is it at least
It's-
assimilating the earlier stuff? Because it looks
There's no
surprising.
assimilation. It's just given a model simulation of Hurricane Bill, compute what the cloud-sat reflectivities would have been given that model simulation.
Wow,
Yeah.
okay.
So it's the fact that it's this close. I'm super happy with that because I've seen it be way not close. Yeah. So we're really excited about this. The rest of the assimilation community is really excited. I mean, I've got people like begging me to get the code and start doing direct assimilation because previously what they would do, like folks like Shuguang, Wong, and OU and others, they would assimilate some retrieved product from radar, like vertical velocity or something, and then they would call that a radar retrieval. But for the first time, this will allow them to directly assimilate the reflectivities. And they're even more excited about what's coming in the future is ground-based radar capabilities from CRTM. So you'll have a physically consistent, space-based, passive, and ground-based capability from one radiative transfer model for your data assimilation framework, or a retrieval framework. CRTM can work for retrievals just as well as it can work for DA. But DA is just a fancy retrieval algorithm, actually, in some sense. All right, well, this is an example of alto cumulus undulatus, so a lot of variability in there. So again, just kind of showing off a little bit. You can see that we're still overestimating the reflectivity compared to the observations, but this is, I was super excited to see this personally. All right. So for those aerosol folks, we've been expanding aerosol capabilities of CRTM very rapidly, right? It initially started off with what you see over there on the right side and the left side here is just some broad categories that were based on go-kart, aerosol model, right? So this just kind of lists the structures of CRTM. You can see there's a wide variety of default capabilities, but now we've started adding additional capabilities with the newer version of CRTM, and those are all listed here. So there's many different aerosol models out there, and we started incorporating them in CRTM, basically to allow our operational folks to be able to choose which model that they would like to use most. And you can see that there's different species in these different groups that you can choose from. Each has its advantage and disadvantage, but for those of you who might be doing dust work, you might want to use, the Navy NAPS model, for example. Or if you wanted to compare it to the Europeans, you might want to use the RT top models that we've imported into CRTM, just so you can do an apples-to-apples comparison. So given this type of information, we've also started doing some LiDAR studies, space-based LiDAR. It's structurally similar to radar. LiDAR, of course, is at a much shorter wavelength. And so what this, just the short story here is that this is observed backscattering coefficients. And so the CRTM can produce something, of course, not with all the noise that you might see in an observation, but based on sort of the physical state of a model, you can produce something that's roughly consistent. LiDAR is much harder to do in simulation, but we're trying to get there because we want to allow people, for the same reason that we did radar, to directly simulate LiDAR observations so they can get at clouds and aerosol properties more directly. So more simulations, that's upper right-hand corner is the MERA-2 reanalysis data set of extinction coefficients calculated directly from the data set, and then the CRTM extinction coefficients, and then updated with this new LOPS map extinction coefficient work. This work kind of stopped because it was a visiting scientist, but we'll be picking it back up shortly to have a future release of CRTM. All right, so we've talked about clouds, we've talked about aerosols, but probably perhaps the most important part is the surface. It's like, how do you characterize the surface, right? That's where most of your radiances are coming from typically. You have emission from the surface, and you learned about this in the radiation class. What this is showing is work by Nick Nolly, who is a former Wisconsin alum. And the black lines here are the default CRTM. That's what's in CRTM now. The varied blue lines here are what Nick's added to give us a broader range of variability for different viewing angles and for different temperatures. So it's basically adding a temperature dependence to IR emissivity. Again, giving us a wider range of variability in our ability to simulate radiances. That way the NWP applications can take more observations and do more with those expensive satellites that we're producing. Also for snow cover, this is a very busy plot, so I'm not going to explain it in detail, but what this is this is a new snow emissivity model, which is showing for various viewing angles of that snowpack, that's what the different lines are here, that you get a much stronger response than the default model, which is, this is our current default model. So you can see that there's a huge new set of information that we can extract from observations of snow cover in the infrared compared to what the default is in CRTM currently. And that's the value of the community model, right? People come in and say, look, I know how to do this. I've been doing this for years. I can just put this in, right? They don't have to learn anything else about the CRTM. They just know how to do snow emissivity. And it's simple. It's a NetCDF file. They just give us the NetCDF file. We massage it to the format that we want, and we give that to the community. They can write papers and get funding, right? And that's exactly what's happening here. And then the non-LTE model is really happening higher up in the atmosphere. It's whenever the kinetic temperature differs from the vibrational temperature, you get an enhanced emission from these higher vibrational temperatures that you don't get at the lower parts of the atmosphere. So it's basically just an additive term. Zhonglong, is Zhonglong here? Zhonglong Li here in this building has been working on similar work as well. So if you have questions about NLTE or if it's something you're interested in, he's really the local expert to talk to on that. And we've been working with Zhonglong and Agnes on a project to start incorporating Zhonglong's model into the CRTM. Just to give you an idea of what kind of differences you might get from NLTE effects. These are wave numbers here for errors, and these are the channels that are impacted by this NLTE effect. Daytime only. Observed is the black line. Red is the NLTE version of CRTM. Is quite close. But if you assume local thermodynamic equilibrium for all of your channels, you'd be missing about 10 to 15 Kelvin of radiance there. So that's a huge error. So these kind of corrections are all part of this sort of package to be able to accurately simulate what your sensor's seeing. All right, so just a bit on how CRTM gets used in the NWP framework. There's something in the Joint Center for Satellite Data Assimilation called the Unified Forward Operator. It's basically a collective effort to take all of the federal agencies, NOAA, NASA, Navy, Air Force, and have them all use the same model to do simulations, right? And the CRTM is the centerpiece of that. Here's an example of AMSU-A, for those of you familiar. This is a microwave sounder. Global picture, you see land, ocean. Some areas are screened out just because of the way we use the data. This is the observed value, so actually from the satellite it's been gridded. And this is what CRTM simulates. So we can really get quite close over land, ocean, if everything is well characterized. And here's the difference between those two. This is what we call an OBS minus background, or O minus B. It's basically this observation minus the simulation. And so typically, globally, we can get sort of in the plus minus 5 Kelvin range for simulations. That includes sea ice, land surface, but there's some things that get missed, like these areas that get QC'd out. That means we're not doing a good job there and they get thrown out well ahead of time. So that these are areas where work needs to be done. So high altitude, ice, desert, jungle, so typical trouble spots, the Himalayan plateau, Siberian permafrost, that kind of stuff. So there's still biases there, and the more science that we can do to improve these biases, the more the data has impact on weather prediction, on forecasts. And this stuff gets used every day by the forecasters. Not this directly, but they'll look at radiances simulated from CRTM. They'll look at retrieved products. They'll look at their, the forecast model output, which depends on the CRTM, to modify that just from the model data. Just a quick note for those of you who are into this stuff. So CRTM version 2.3, that was a previous operational version. For this particular case, it assimilated this number of observations. With the newer version, we added, about 100 more observations. That seems like a small improvement, but in NWP, a 1% improvement is actually substantial. Most of the time, they're looking for neutral impact when you change something. They're happy if nothing changes, actually. So any positive modification like this is really impactful. And so that's that slow crank that we're constantly turning, and that's where your innovations, you're seeing something, you're like, I know how to do that. I know how to fix that problem. It could immediately be impactful in an operational system. And then just to give another example of that, this is ATMS channel 3. These are the observations. These are the simulations from CRTM. Again, the same issue. And then if you look at the difference, you'll see a few things that pop out. So these blue areas here over the ocean, those are clouds. That means that we're not doing a great job in the clouds there. It could because we just missed it completely, or because we're assuming the wrong things. You also see some differences over the sea ice, over land, over mountains. So some of the usual suspects are there, and that's where the most challenging, where the things change the most, or where they're the most complex, that's where it's also the hardest to simulate accurately. Rough terrain, precipitation, because it's nonlinear, it changes rapidly, and it's hard to model. So these are the kind of areas that need attention, that need focus, and it's going to be many of you in this room who work on these kind of topics in the future, and hopefully lead to some improvement. So you can help, literally can help. So I've listed several things here. I'm not going to read through all of them. But if there's something here that you're like, you know what, I have an interest in that, it's something that I want to do for my PhD, or even after PhD, something I can contribute to, knock yourself out, right? Come talk to me. Happy to set you up with a GitHub account, tell you how to start contributing right away. Super simple. And even if you're just into coding, like just code optimization, porting to a GPU could speed things up by a factor of 1,000 or whatever, so like taking advantage of that. Or even AI models, so we're starting to get to this revolution in AI, and some of you agree, some of you disagree, but the truth is that we're already seeing it, is that we can use an AI model to train against CRTM and run super fast, 1,000 times faster than CRTM can run right now. That could be our front end, and then we can slow CRTM down on the back end and make it a lot slower and train against that constantly, right? So it can become more of a research model. Right now, I always have to balance accuracy and speed. Speed always has to win because it's an operational model. It has to run within that 20-minute wall clock time for operations, right? But if I can disambiguate that part, I can have a really slow research model, a really fast AI model that runs operationally, that's a win-win situation. Right? They don't care that you're running the actual native CRTM model in operations. They just need something that's going to get you really close to the observations, right? So it's these kind of things, or even internal things that could be replaced by AI. It's not a solution to everything, obviously, but it's a tool, and it's a tool that can be used very effectively, and I've seen it already. So you can get involved too. I have a user developer workshop every 2 years roughly. We have a summer colloquium, hopefully coming up this summer, although the pandemic's kind of messing things up. We haven't settled this date yet. This is typically where, have any of you participated in a JCSDA summer colloquium ever? Okay. This is typically where the students come. So we get graduate students from various universities like Wisconsin, Colorado, Penn State, Florida, Washington, so on, who come and learn about data assimilation and learn about CRTM, modeling, and so on. We also have code sprints where people want to get together and really hack on code for about a week or so. We just lock you in a room with some coffee and donuts and really go into something that's really challenging. That's been very useful. Seminars and colloquia, obviously, I'm involved in a number of groups. And I recommend that you start getting involved in these sort of international groups where all of the experts of a particular topic get together and start having workshop type discussions. I also do a lot of outreach too, mentoring some middle school students in the Science Olympiad. So, you know, as a scientist, I take my role seriously as as somebody who's supposed to be spreading the gospel, let's say, and letting people know about. I don't go and talk to the middle school students about CRTM, of course, but it's just to help keep that interest level up, especially for young women. It's been hard seeing even my own daughter, who's 13. She's kind of pushing away from science a little bit. Trying to keep her interested, but not too interested. You know what I mean? Like, I can't force it. So it's these kind of things that make sure that we have folks who are continuing to have an interest in science and weather and things like that coming up through the ranks. And start in a little bit early here, but please feel free to send me email anytime if you're interested. There's no stupid questions. Just shoot me an email saying, hey, can CRTM do this? Or can I contribute to this? I'm happy to help. Thanks. Any questions?
So I'm taking over the MC duties, but we've got a few minutes for some questions for Ben.
I realize I talk fast. I get that from them, so.
I think you did that on your own. Norm.
Yeah, so I'm thinking about, from the perspective of this being a 1D model, plane parallel.
Yep.
So as you work toward observing systems that have larger footprints, larger fields of view, is there any need for some sort of treatment for subpixel cloud precipitation variability? Would that be? I know there are techniques for doing that on the flux model side, but I'm not sure what that would involve with the radiance model.
Yeah, absolutely. So CRTM doesn't know anything about horizontal variability because it's a 1D model. So you could apply it at multiple subgrid pixels. It doesn't know anything about the field of view either, which may or may not be an issue depending on how you look at it. But it does try to simulate, given a path of optical properties, what would the radiance be? So you can imagine 1D doesn't mean you're limited to vertical. So you could trace a 1D line through any 3D domain and collect the properties along there and still do the calculation if you're careful about how you accumulate the optical depth. You just have to be careful about the little bit geometry argument. But that's how we're going to do slant path radiative transfer, is just by projecting a line through a different part of the domain and collect that and produce the radiance. But for the 3D effects, especially as model resolutions get closer and closer to resolving convective scales, that's when it really starts to pick up, because you might have emission from the side of a towering cumulonimbus cloud or something like that, right, that you have to account for in the 3D case. And Grant's written papers on this, that impact of the 3D versus 1D. So it's important. It's not important to operations right now because we're still at the 100-kilometer scale for global, but we're getting closer. And the physical parameterizations have to catch up too on the model side in order to do this well. So my philosophy is to stay ahead of the curve in terms of capability, so that whenever the model sides are ready, CRTM's already ready to simulate that.
Let me go ahead and jump on Norm's question because it kind of anticipated what I was also going to ask, so I'll just make them fit together. So we talked about the slant path radiative transfer as kind of a pseudo 3D approach, where you're basically tracing slant paths through it, presumably looking at reflections into the side as well. There's that, which is kind of pseudo 3D, and then there's actual 3D effects that can't be accomplished in that manner. And my question is basically, has there been any evidence that that is a significant source of bias or disagreement with real observations, where you might think, well, maybe this would be better agreement if we were actually capturing the three-dimensional structure of the clouds?
There is evidence in some specific cases where that would be an impact. However, for numerical weather prediction, it's not enough of an impact to warrant the effort required, and the amount of the computational costs associated with a 3D model versus a 1D model is substantial. So that's the trade-off thing again. It's like, okay, where's this trade-off space? And that's where a potential AI model could actually help us disambiguate that, and then we could have a really complex, highly detailed radiative transfer solver that we train an AI model against and help to mitigate some of that. But yes, but does it rise to the level of something that we want to spend time on and that our operational users would take?
Any other questions? Andy?
Yeah, you mentioned, I know in the old days, CRTM used to have multiple solvers.
Yep.
Is that still the
Yeah.
solution? So they're still working on
Yeah, so
speeding up solvers?
I guess Tom Greenwald's not here, I don't see him, but I talked to him earlier today. So Tom wrote an additional solver for CRTM, which is the SOI, successive order of interaction solver, which CRTM still uses. It'll switch between this something that's like a doubling adding model or to the SOI model, depending on what the scattering properties are. So it does switch between those two, and you can add additional solvers to it too. There's a solver module. You can just drop in different solvers. So you could put a Monte Carlo solver in there or something if you wanted to. If you really wanted to get crazy.
But, so the AI, there's a lot of ML and AI work to speed up solvers. Is that something you guys have on
Absolutely. So there's already been work done in STAR that's done single sensor AI simulations of, to replace CRTM. Not to replace it, but to simulate what CRTM does. They find they're getting about 100 times speed up over CRTM for the same calculations with roughly, there's always some accuracy hit that you take. It's not bad. The challenge has always been the Jacobian. So getting the first derivative using an AI method, that's a bit challenging because it's really, really sensitive to what AI method you're using, how you're training the data, and so on. So that's a bit more of a challenge. So if you're just doing sound light simulations, perfect, easy solution. But if you're doing it for NWP, you need that Jacobian, that derivative, and that's a bit more challenging. Although newer AI technologies provide you with Jacobian as part of the process. So enterprising graduate student, postdoc can take that and run with it, and that's a PhD. Easy. Yeah.
Other questions? In that case, thank you very much for being here.